to spend a couple of videos talking about some of the things Ptolemy proved. The first thing that I want to show is how he was able to compute chord 36. Okay, so the chord for the angle being 36. Now, if we think about this, what does this correspond to? Well, 36 times 10 is 360. So chord 36 is equivalent to saying the side length. So if you have a circle, okay, for a given radius, chord 36 is going to be the side length of a decagon inscribed in that circle. Decagon has 10 sides, which means there's 10 angles. 10 times 36 is equal to 360. So a chord 36 is the same as the inscribed length of a decagon. Or sorry, the side length of an inscribed decagon. Okay, now to prove this, I'm going to mention a couple of facts from Euclid's Elements that I didn't know about these before. So I'm not gonna explain why these are true. These are from the Elements, so we're just gonna take them as given. So the first thing is going to be the following. Maybe I can write it up here. If you have a line segment like this. So several times in the book, it talks about dividing a line into extreme and mean ratio. This just means the golden ratio. So let's say we have a line segment A, B, C. We say that the point C divides the line segment into equal and mean, extreme and mean ratio, or the golden ratio, if the following is true. If AB divided by CB if AB divided by CB is equal to CB divided by AC, then we say that C divides the line into extreme and mean ratio, or the golden ratio. Okay, now what Euclid proves is that in such a case, AC is going to be the side length of a decagon, and CB is going to be the side length of a hexagon inscribed in the same circle. Okay, so if you have what he proves is that if you take a hexagon and a decagon, the side length of a hexagon and the side length of a decagon that are inscribed in the same circle, okay, then and put them next to each other, then this line segment, the decagon length, so and you put them together, then the decagon length is going to divide this line segment into extreme and mean ratio, or the golden ratio. Okay, so that's the first step. What he says is that if you take a circle with an inscribed hexagon and an inscribed decagon, then and put them together in a line segment like this, then the decagon line segment is going to divide the whole thing into the golden ratio, or into extreme and mean ratio. Okay, now let's think about this. Okay, so what is the relationship between a hexagon and the radius of a circle, or the side length of a hexagon and the radius of a circle? Well, I showed this before, but let me do it again. Okay, for a hexagon, let's say this is 60 degrees. A hexagon has 6 sides. 360 divided by 6 is 60. So these are going to be 60-degree angles here. This distance here is R. This distance here is R. So then we have an equilateral triangle. So this right here, which is chord of 60. So chord 60 is the same as the side length of a hexagon. It's going to be an equilateral triangle. Well, if it's an equilateral triangle and this side length is R, it means this side length also has to be R. So then what you can say, anytime you have a line segment divided in extreme and mean ratio, this right here is always going to be the side length of a hexagon inscribed in a circle with that radius, which means that's always going to be the side length of a decagon inscribed in the same circle. Okay, so that is the first piece of information that we're going to use from Euclid. Here's a second piece of information that we're going to use, and I'm going to use it using letters that are going to be consistent with what I do on the picture here. So let's say we have a line segment. Actually, let's start with a line segment like this. I'm going to label this as D. I'm going to label this as C. And then E bisects this line segment. Okay, so we have this line segment divided in two. And then let's say we add some other line segment like this. This is F. What Euclid proves is that if you look at the rectangle whose side length is this entire side length and whose height is equal to df, this is not to scale. If you look at this rectangle, so its area is going to be equal to FC times df. I'm not so worried about the order of these letters here. I could probably stay consistent, but I'm not. So sorry. If you do this, and then you look at the square on half of the line, so something like this, so plus EC squared, then it is going to be equal to the square that you get if you take the added line segment and half of the line segment. So this is going to be equal to EF squared, like this. Okay, again, this is a fact that Euclid proves, and I'm just going to take it as given to give this argument that Euclid gives for chord 36, which again we can recognize as the side length, of a hexagon, a decagon inscribed in a circle. Okay, so let's do something like this. Let's label. We're going to call this point the center of the circle is going to be D. This point here is going to be C. This point here is going to be A, and we're going to draw a line straight up to the top of the circle, B, and this is going to be a right angle. I'm going to look at a point E. Okay, so E bisects this line segment from D to C. So E bisects that segment. And now we're going to look at a line segment going from B to E. And now we're going to pick a line segment or a point over here, F, such that the following holds. We want the line segment from I forget what this is. We want the line segment from E to F to equal the line segment from E to B. So we want the distance. So we choose F. So we choose F so that the distance from E to F is equal to the distance from E to B. Okay, so in other words, we kind of like take this and put it there, and that's what F is going to be. Whatever that length is there, that's what that length is going to be here. Okay, so how can we, what are we going to do next? Well, we're going to apply this thing that I just mentioned over here with all of these letters basically being the same. So CD is bisected by E, so DEC, like this right here, corresponds to that, and then this FD corresponds to this. Okay, so what can we do with this then? What it tells us, again, using the letters that we have on the board, and maybe I'll try to make try to put the line segments, their letters in alphabetical order just to have some sort of uniformity here. So CF times DF plus CE squared is equal to EF squared. Okay, so we can rearrange this and get that CF DF is equal to EF squared minus CE squared. EF squared minus CE squared. Okay. Now CE, so what I want to do, I've got EF squared minus CE squared, and this looks like Pythagorean theorem E, and I've got a right triangle, so I'm going to somehow make EF squared minus CE squared. I want to recognize EF as being the side length of a triangle, like the hypotenuse of a right triangle, and CE as being the leg of that same right triangle. Well, this is good because EF is chosen so that EF is equal to EB. And look, EB is a hypotenuse of a triangle. So this is going to be EB, or I'll do again BE squared to keep the order. Now what about CE? Well, E bisects DE. Or sorry, E bisects DC. So then CE is just equal to DE. So this is minus DE squared. Okay, so then by the Pythagorean theorem, BE squared minus DE squared is equal to BD squared. Well, what is BD? BD is just the radius of the circle. So then BD is equal to CD. So this is equal to CD squared. Okay, so I'm gonna erase all of this because I just want to write this is equal to CD squared. Okay, so CF times DF is equal to CD squared. So CF times DF is equal to CD squared. So CF times DF is equal to CD squared. Okay, now if we rearrange this, notice what's going to happen. I've got CF, that's this distance here. I've got DF, that's that distance there. And I have CD, which is this distance here. So if we rearrange this, if I divide both sides by CD and DF, I have CF over CD. So CF divided by CD is equal to CD, that is CD over DF. Okay, so CF over CD equals CD over DF. So CF over CD is equal to CD over DF. In other words, this point D divides this line segment from C to F into extreme and mean ratio, or the golden ratio. Okay, so what this means is that CD is going to be the side length of a hexagon, and DF is going to be the side length of a decagon inscribed in the same circle. Okay, well, CD, that is the radius of this circle. So what this means is that CD is the side length of a hexagon inscribed in this circle. So then DF is a side length, excuse me, so then DF is a side length of a decagon inscribed in this same circle. So again, DF or FD, however you want to say it, is a side length of a circle. Sorry, FD is a side length of a circle inscribed in the same. DF is the side length of a decagon inscribed in this same circle. So sorry about that. I got a little tongue-tied there. Okay, well then how can we relate then DF? I mean, okay, so that's great, but we now need somehow to compute what the length of DF is. Okay, and again, we can use various, trigonometry facts here. Okay, so we can write DF in the following way. DF is a difference. DF we can look at as the distance of two other distances. Okay, so let me see where I want to erase here. So DF is equal to EF minus DF is equal to EF minus ED. EF minus ED, or let me do DE to keep the notation. Okay, so EF is equal to DF, which is the length of the side length of the inscribed decagon, which is equal to chord 36. So DF is equal to EF minus DE. Okay, so we see that. But now what is EF equal to? Well, EF is just equal. Remember, EF is chosen so that this is equal to BE. Okay, so EF is equal to BE. Sorry. EF is equal to BE. And then minus ED. or minus DE. Okay, well, what are these two things equal to? Well, EB is the hypotenuse of a triangle. So EB is a hypotenuse of a triangle. So EB, or BE the way that I have it here, is equal to the square root of DE squared plus BD squared, is equal to the square root of BE squared plus DE squared, and then minus DE. Okay, well, sorry, this is BD squared. Right, BE is the hypotenuse of this triangle, so that is going to be equal to the square root of BD squared, which is that, plus DE squared, which is that. Okay, well, what is BD? BD is just the radius, so this is going to be r squared. What is DE? DE is half the radius. Okay, so DE is half the radius. So this is going to be r squared divided by 4. And then DE is also half the radius, so this is going to be r over 2. Okay, now for a particular value of r, they were using 60. We can now figure out, okay, so, again, the length, the side length of the inscribed decagon is obviously going to depend on the radius of the circle. They were doing everything with like the standard being 60, with the standard radius being 60. And so when we say chord 36, if we have in mind that we want the radius to be 60, you just plug in 60 here, and that's what chord 36 is. We might be more comfortable choosing r being equal to 1, and we can compute this to figure out what the chord length is for a decagon inscribed in a unit circle. But they're doing a decagon inscribed in a 60 unit circle. That is a circle whose radius is 60, and you can plug in 60 there and figure out what chord 36 is going to be. Okay, so that tells us that tells us how to find chord 36. Okay, so